At 200 miles per hour, an F1 car isn't just driving, it's flying upside down. Every flick, fin, and curve on the chassis is there for one reason: to bend the air into submission. It's not about looking fast, it's about controlling the invisible. Aerodynamics isn't magic, it's physics, specifically pressure differentials. Air doesn't push, it flows. When it flows faster over a surface, it creates a region of low pressure. When it slows down, pressure rises. An F1 car uses that principle everywhere. The faster air goes over one surface, the more it sucks the car downward. That's downforce. Not a wing pushing down, but air pulling it to the ground through pressure difference. Every part of an F1 car exists to manipulate that difference. The front wing, floor, diffuser, sidepods, beam wing, all designed to sculpt the airflow to generate maximum downforce with minimum drag. That's the holy grail: high downforce, low drag. The perfect contradiction F1 engineers spend their lives chasing. The front wing is the single most important aerodynamic component on the car. It's not just generating downforce, it's setting up the entire airflow pattern for everything behind it. Modern front wings have 5 main elements, each controlling airflow over and around the front tires. Those massive end plates you see, they're not just cosmetic, they're vortex generators. As air hits the wing, it splits into 3 major paths: over the wing, low pressure, front downforce. Around the tires, controlled vortices to prevent turbulence. Under the floor, the foundation for ground effect. The front wing's job is balance. Too much downforce and drag skyrockets. Too little and the front end washes out in corners. So teams use adjustable flaps and pressure sensors to tune the balance, sometimes by as little as 0.2 degrees, to find that perfect flow structure. Even a chip from debris can destroy that balance and cost half a second a lap. Most of an F1 car's downforce doesn't come from wings, it comes from underneath. Ground effect works by accelerating air under the car through a venturi tunnel, a narrowing channel that speeds up airflow and drops pressure. That low-pressure region literally sucks the car to the track. The faster you go, the stronger the effect, until the car's so low that the airflow chokes and stalls. That's why ride height is everything in modern F1. A change of just 2 millimeters can shift balance, reduce downforce, or cause porpoising, that bouncing effect from unstable airflow under the floor. Teams spend hundreds of hours in CFD and wind tunnels trying to control that flow. They use flexible floors, edge wings, and strakes to seal the underbody, keeping the venturi tunnels fed with clean, high-speed air. The goal? Maximum suction, minimum stall. The diffuser at the back of the car is what finishes the job. Air rushing under the floor needs to slow down and expand as it exits, and the diffuser controls that expansion. By creating a controlled expansion zone, it helps maintain low pressure under the floor for longer, keeping the car stable. The steeper the diffuser angle, the more downforce you can generate, but if it's too steep, the airflow separates and stalls. That's why modern diffusers use strakes, vertical fins. They organize and energize the flow, delaying stall and stabilizing rear-end grip. When it's done right, the diffuser adds hundreds of kilograms of downforce with almost no drag penalty. Look closely at the side of an F1 car, it's chaos. Curves, cutouts, turning vanes, and floor edges all working together to manage vortices. A vortex is a mini tornado, rotating air that behaves like a barrier. Teams use them to seal the floor, keeping high-pressure air from leaking underneath and ruining ground effect. Before 2022, barge boards did that job, slicing and spinning airflow around the sidepods. Now, with simpler bodywork rules, the undercut sidepods and floor edge wings do the same job. Each vortex can carry hundreds of liters of air per second. Invisible, but crucial. Get it right and you gain stability. Get it wrong and the floor stalls, killing rear grip instantly. The rear wing is the final piece of the aerodynamic puzzle. It provides the majority of rear downforce, balancing what the front wing creates. Its main plane and flap elements form an airfoil that accelerates air over the top, lowering pressure and forcing the car down. But with it comes drag. That's why DRS, drag reduction system, exists. When DRS opens, it flattens the rear flap, allowing air to flow freely and reducing drag by up to 25%. That gives an F1 car a top speed boost of 10 to 12 kilometers per hour on straights. But the trade-off is stability. Without that flap-generating pressure, the car becomes twitchy under braking, which is why DRS is only allowed in specific zones. Rear wings are also finely tuned for track-type, high downforce setups for Monaco or Hungary, low-drag trim for Monza or Baku. Every angle, every millimeter of end plate changes airflow interaction with the diffuser below it. It's not just a wing, it's a pressure management system tied to the entire car. An F1 car doesn't have one airflow. It has hundreds of interacting layers. Upper flow, over the chassis and halo, feeding the rear wing. Mid-flow, around the sidepods, managing cooling and drag. Lower flow, under the floor, generating ground effect. All three interact. What you do at the front dictates everything downstream. That's why F1 cars are designed as systems, not parts. Change one element, say the nose shape, and airflow to the floor, diffuser, and rear wing all shift. That's why updates come in packages. The most powerful tool for this is CFD, computational fluid dynamics, virtual wind tunnel simulation. Teams model flow in billions of data points, measuring pressure, velocity, and turbulence with microscopic precision. It's digital aerodynamics, where every idea is tested before a single part is built. Aerodynamics isn't just about downforce, it's about temperature control. Engines, batteries, and brakes all need cooling, but airflow through radiators adds drag, so every inlet, duct, and vent is a compromise between cooling efficiency and aero efficiency. Tight side pods reduce drag but limit cooling. That's why Red Bull's Coke bottle shape is such a masterpiece. It directs airflow tightly around the engine without choking it. Teams even use fluidic switches, passive airflow devices that open cooling paths only when pressure builds. It's invisible, automatic, and aerodynamic art. Aerodynamics isn't static. Cars move. When an F1 car turns, it yaws, and airflow doesn't hit the surfaces head-on anymore. That's why engineers obsess over yaw sensitivity, how stable downforce stays when the car's sliding or cornering. Roll, side tilt under cornering, also changes ground clearance, altering the Venturi effect under the floor. And ride height changes with speed. As the car compresses under downforce, airflow patterns shift dramatically. That's why suspension and aero teams work hand in hand. Every spring rate, damper, and heave element affects airflow control. It's not just suspension tuning, it's aero tuning through mechanics. When a car moves through the air, it leaves a wake, turbulent air filled with low-energy vortices. That dirty air makes it harder for the car behind to generate downforce, especially on the front wing and floor. That's why overtaking in F1 was nearly impossible for years, until the 2022 ground effect regulations. These new rules simplified the topside aerodynamics and moved downforce generation under the car, drastically reducing wake turbulence. Now cars can follow within 1 second with only approximately 15% downforce loss instead of 40%. It's the biggest aerodynamic improvement to racing in 20 years, and it's all about cleaner airflow structures. Wind tunnels are still the final word. Cars are tested at 60% scale models under strict FIA limits, 400 runs per week max. The models sit on rolling roads with moving belts to simulate tire rotation and boundary layer effects. Engineers map out pressure coefficients across hundreds of sensors, comparing real-world flow to CFD data. Every result feeds back into the next simulation cycle, an endless feedback loop of digital versus physical. Even with all the computing power in the world, nothing replaces actual air. All of F1 aerodynamics comes down to one ratio, L/D, lift to drag. Lift is downforce, drag is resistance. The higher the LD ratio, the more efficient the car. For reference, a road car, L/D approximately 0.1. A GT car, L/D approximately 2.0. An F1 car, L/D over 5.0, 5 times more downforce than drag. That's what lets them corner at 5G while still hitting 220 miles per hour on straights. But it's a knife's edge. Every millimeter of aero setup, from flap angles to rake height, changes that ratio. That's why setup days in F1 aren't just about suspension, they're about fluid dynamics. Aerodynamics isn't about airflow, it's about control. Every curve, every fin, every millimeter of carbon is there to manipulate invisible forces into speed. It's what turns chaos into grip and grip into victory. And if you want to understand how cars evolve through performance levels, from road machines to track-bred perfection, go watch The 7 Levels of Car Explained in Detail. Because whether it's Formula One or your daily driver, every machine lives somewhere on that scale, and the higher you go, the more every atom of air starts to matter.